All right, so today we're starting section 6.1, which is verifying differential equations and finding particular solutions. Now, I know some of you are math majors, or you've got some kind of a double major with math, or have a math minor. We actually have a class at our university, and this is very typical for a math class. It's called Differential Equations. So as you're looking forward, those of you who are taking more math classes after this one, differential equations is going to feel like this at the beginning. So this kind of gives you a taste into that, that course as well. All right, so to talk with first, I'm going to talk about what a differential equation is. A differential equation is an equation involving x, y, and y prime. Okay, so not just x and y anymore. We've got all three of them involved, potentially. It's a solution of the differential equation is a function y equals f of x that satisfies the differential equation. Now, one of the first things you learn to do when you're finding solutions of systems of equations, right? So systems of equations might look like two lines. One of the very first things you do back in algebra when you're learning about that is they give you a point and they say, is it a solution, right? And the way that you test whether it's a solution or not is you plug it into one equation and you see, does it work? You plug it into a second equation and you see if it does it work. And if it works in both of them, it's a solution. You guys remember that? That was very, very first end of anything you were doing with systems of equations. Well, this has that same sort of feel to it. We have a potential solution, and in fact, we know it is because it has this word verify. Whenever you see the word verify, it means it's going to work. You just have to show it works. All right? So be aware of what the words are in the problem that you're dealing with. This one says verify that it's a solution. And then we have something that is the differential equation. Our differential equation is 3y prime plus 5y equals negative e to the negative 2x. All right, so if you're taking a look here, we have something in terms of x on the right already, right? So there's nothing to do here. This middle piece right here says 5y, and we know what y is. It's this e to the negative 2x, so we can substitute that in there. What in the world are we going to substitute in for y prime? I need to take the derivative of y in order to get that, and that will be what I substitute in. So my very first step in what I'm doing here, so my very first step is to take the derivative of the solution that I have been presented with. All right, so what is the derivative of e to the negative 2x? E to the negative 2x, what else? Times negative 2, and I'll put it in front, so it's right there. Everybody good with that? So we have this piece, which will go in for y prime. We have this piece that'll go in for y. And that's what we're going to do. We're going to do just like you did in algebra. We're going to plug things in and show that both sides of the equation equal each other. All right? So we have 3 times negative 2e to the negative 2x plus 5 times e to the negative 2x. And my goal is to show, I'll put a question mark here for right now, that this really does in fact equal negative e to the negative 2x. So how do we show that in fact it does? Well, what we don't do is we don't move anything between sides of equation. Okay, guys, this should feel a little bit like when we did trig verification. So you're just working with one side of the equation at a time. The right-hand side's already simplified, so we're just going to simplify what's on the left and verify that it really works. So if I have negative 2 times 3, I've got negative 6e to the negative 2x plus 5e to the negative 2x. And what does that equal? Yeah, I've got negative 6 of them, positive 5 of them, so this is negative e to the negative 2x, which equals the negative e to the negative 2x on the right, and it's verified. Does that make sense? All good with that? All right. We're going to do another one. What's different about this one? There's several things. Somebody tell me one. I've got a second derivative here. What else? Trig. There's trig involved. And we've got a natural log. But I want you to look carefully at this piece and tell me that you've seen it before. Okay, where have you seen it? This is the antiderivative of secant, and that is really important here, because when I go to take the derivative of y, I do not want to take a derivative of a natural log of secant x plus tangent x. Do you? It's going to become really messy. But if I recognize that that piece is really the antiderivative of secant, then it means that the derivative of the natural log of secant x plus tangent x is secant x, because that's the relationship between derivatives and antiderivatives. So don't just barrel on there through with all of your fun rules with chain rules and product rules and things. Take a minute to look at that and recognize on some of these, does that look like something I've seen before? Because it'll help you out in the long run. Okay, so Stephanie mentioned I have a second derivative, which means I'm going to have to find the first derivative and the second derivative. So let's start that with the first derivative then. All right, first derivative. What do you notice besides this antiderivative of secant? It is a product rule. And some of you still really want product rules to be the product of each individually, okay? But it isn't, right? I wish it were too. It'd be so much easier. Life would just be so much easier. But it isn't, so what do I do for the product rule of these two pieces? Oh, you guys are just all talking at once. Don't know what to do with that. All right, so how about we do the same thing all together? Can I leave the first one alone? Is that okay with you? All right, I know some of you do it the other direction. If you want to, that's fine. But I'm going to leave the first one alone. And that means then what I need to do with the second piece? Take the derivative. And we already know what the derivative of the second piece is. It's what? Secant x. All right, so this is secant x. And I don't know about you, but I like multiplying secant and cosine. In a minute here, you'll see me do it. Because what is it going to become? 1. Yeah, well, -1 because I've got a negative cosine. But yeah, it's 1 when I'm multiplying because they're reciprocals, right? Okay. All right, so we've got half the problem done, and then we need addition, right? All right, now we are going to take the derivative of the negative cosine x. So what's the derivative of negative cosine x?
Sine x.
That's actually positive sine x, isn't it? And then I'm going to rewrite the second piece as it is. So this is one of those things, whenever you learned about second derivatives that you did, is you said, okay, we have to simplify this, not just because, hey, we should simplify because we should, but because it's going to make the next part easier. So you guys already told me this should be -1, and then I have plus sine x times the natural log of secant x plus tangent x. And we're ready to take the second derivative. All right, so what's the derivative of the -1? 0, good. And then we need the derivative of the sine x times the natural log. So this really looks almost like what we just did, isn't it? All right, so the first thing I'm going to do is I'm going to write down my sine x. And then what is the derivative of the natural log of secant x plus tangent x? That is secant x. All right, and then we have to take the derivative of sine, which is cosine, and then rewrite the natural log. Can we clean up that first piece so that, because we're going to be plugging something in, evaluating, what is sine times secant? Tangent. That's actually tangent, and if you aren't sure, weren't looking at that and thinking about this, this is 1 over cosine, right? So sine over cosine is equivalent to tangent. So this is tangent x plus cosine x natural log of secant x plus tangent x. All right, so look back at that differential equation. That differential equation does not actually involve y prime at all, does it? So we really don't actually need that piece for purposes of verification. We just had to do it as an intermediate step. So we need to take that new second derivative that we got down here, this piece right here, and we're going to plug that into y prime, double prime, sorry. And then the original values that we had up here for y get plugged in here for y, and we are supposing and hoping that when we add those together we get tangent. And I think we will. So we're going to do that next. And I think I'm going to need, no, I've got to use the same screen. That'll work. All right, so what I'm supposed to be doing is I'm supposed to put in the tangent x plus cosine x natural log of secant x plus tangent x. and then I've got plus y, and then y is actually a negative cosine of x, natural log of secant of x plus tangent of x. And I want to show that this is equal to tangent x. And it will be, because what happens on the left-hand side? Yeah, these two add together to be 0, because they're equivalent and opposite signs, which means I do in fact have tangent x on the left. I have tangent x on the right. So I can check that off as being verified. So a little bit more complicated than the last one, but the process is still the same, right? You take the derivatives that you need, and then you plug them into the equation to verify that both sides are equal. All right, number 3, or number 2, example number 2 here on my verification, is done a little bit differently. It doesn't say the same directions as the one before, and it's got a little bit extra information. So tell me, what do you see different about the directions first? Still says verify, but what's different? It says particular solution. And what do you see different about the information you're given? We've got a specific value, x, y coordinate pair. When x is pi halves, y is 1. Right? That's what where y of pi halves equals 1 means. When x is pi halves, y is 1. So this has sort of an innate sense of there's an extra step here. Can you kind of feel it? I've got extra information. There must be an extra step going on. And there is. The extra step going on is that we actually have to verify that the solution that we have, where it says y equals e to the negative cosine x, actually has the property that when I plug in pi halves for x, I get 1 for y. That's the extra step. But I still have all the same steps as well as I had before. I still have to find out the derivative and plug it in and so forth. So the first thing we're going to do is going to look just like the last steps. Okay, last two problems we did, part A and B. We're going to find out what is y prime, and we're going to verify it in the differential equation. So what is y prime when y is equal to e to the negative cosine x? Okay, so the e part is still there, e to the negative cosine of x. And what is the derivative of the negative cosine x? Sine x. Most of you were saying that in front, and I'll put it there too. So that's y prime. All right, so I'm going to take this piece then and plug it in on this side, and this piece to plug it in over here. Does that look good to everybody? All right, so I have sine of x e to the negative cosine of x equals e to the negative cosine of x times sine x. And that one was pretty quick, right? Those are the same. We will do one step where we sort of move one or the other to where sine is. Or if you had originally done your derivative right here, where you had written the sine at the end, it'd already be there. But we want the two sides to look identically the same. We don't want anyone to look at this and say, wait a minute, oh yeah, they're just in a different order. They don't need to do that. They just need to look at it and say identically the same, which means for what I'm doing, I'm going to go ahead and rewrite the right-hand side to move the sine to the front. But you could do it the other way around. Okay, they're identically the same. Everybody good with that? Okay, the other piece then is verifying this right here. What happens when we take that pi over 2 and plug it in for x? Into the original equation. So my original solution rather is that I've got y equals e to the negative cosine x. So I need to take that y and plug in pi over 2. So that means I have e to the negative cosine of x. I'm sorry, cosine instead of x of pi over 2. All right, so now you got to use your trig unit circle stuff. What is the cosine of pi over 2? That's 0. So this is e to the negative cosine, I'm sorry, to the negative technically 0, or e to the 0, right? What is e to the 0? 1, which was exactly what we were supposed to be verifying here, right? That when we plug in pi over 2, we get back the value of 1. Because this is not like incredibly more work, right? We just have this one extra step where we're verifying a specific value. Any questions? Okay. This one's directions say something different than we've seen on any of the three so far. What's different? What is it? Determine instead of verify. How is that different? It might not work, right? So if you see directions that say determine and you're not paying attention and you're thinking they say verify and you keep getting something to not work out, you may be spinning your wheels, right? It just flat out may not work out. So pay real good attention to what those directions say because you don't want to waste your time trying to do something it didn't tell you to do. This one says determine, which means that it may not work in the end. So the other thing that you see here is something you may not have seen before, but you might have. Have you seen the notation with this little 4 up here like this? Any guesses as to what it might mean? It is a fourth derivative, okay? So when we do it up to 3 derivatives, you usually see them do the 3 primes. Once you get to 4 derivatives, we're stuck with the primes because this becomes the silliness, right? So we're not going to do 4 primes. You'll see them use numbers like 4 or 5 if you wanted to go higher. But it does mean that we have to do what? 4 derivatives. Thankfully, when I take the derivative of this, there's no product rules or chain rules, so this isn't a difficult one to take 4 derivatives of, right? It's not too bad. Let's take the first derivative of this. What is y prime? Good. Okay, somebody else tell me what is y double prime? Negative 2 sine x. Good. Okay, yet another person. I need y triple prime, or the third derivative. Negative 2 cosine x. Excellent. And now we're ready for this new notation where I've got the 4. What's the fourth derivative? 2 sine x. Which happens to look a lot like what? Yeah, it's exactly y on this particular one. Okay. All right, so we're supposed to use this differential equation now. So I take the y to the 4th that I just found, which was 2 sine of x, minus 16, and I take the y that I was originally given, which was 2 sine of x, and I want to know if this equals 0. What does the left-hand side equal? And what is 2 sine x minus 32 sine x? Negative 30 sine x. And while there are places where this is going to equal 0, does it always equal 0? No, this does not always work. There are certain values for x for which it would work, but in general it does not work. So is this a solution? It is not a solution. And a good thing for you to do right here is to mark that that's not equal. I don't mean it's not equal ever, but it's not equal always. And that's what we were trying to do when we were doing this verification, or this determination. All right, what's different about these directions? We have a point. We haven't, well, we've sort of had a point before, but not written like this, right? What else is different? Hang on just a second. What did you say, Jordan? It has find in there. We haven't had the word find show up yet. And what did you say, Taylor?
It's equal to some
We've got a C in there too, which is also different, right? Okay, so the word find is where I want to focus my attention first. You see, on all of the others, we weren't told to find something. We were given something and told to verify it. So this sort of relates back to when you did systems of equations, right? The first thing you were done is you were given a point and you were asked to verify that it works. And then they start saying, now find the point that works. And you always were looking for where something actually crossed, 2 lines crossed or 2 curves crossed. Well, we're kind of at the point here, except that it still says solution, doesn't it? So that's kind of weird. Why would it say here's a solution, but then it says find? Any thoughts?
It says check. On ours it says check no solution.
What does it say?
General solution.
Mm-hmm.
It's not for every single.
Yeah, so on your page, there's a little bit more information than is on my screen. It probably had to do with me writing it in. You have the word general right here, right, Janet? This solution is a general solution, and it goes back to what Taylor said of that C on the right-hand side. This isn't a solution, it's a general solution because I'm sort of missing whatever that constant is. I don't know what it is. Okay, so there's two things here. What we're going to do is we're going to find out what the general solution will become with this extra condition. I know that when x equals to 0, y is supposed to equal to 3. Can I figure out what C would have to be to make that happen? I should be able to. How could I do that? Yeah, I can take this equation right here and I can plug in the x value and the y value to find out what C should be. So I have 2 times 0 squared minus 3 squared equals to C. What is C? It's negative 9. So the particular solution would be, I'll put a colon there, would be 2x squared minus y squared equals negative 9. Notice what it didn't do. It didn't actually tell you you had to verify that it was a solution at all, did it? It told you this is the general solution. They're not asking you to make sure, they're not asking you to check. They're telling you this will work, and here's this condition, sometimes called an initial condition, and they're saying they want you to find the particular solution, which means you're really done. You don't have to verify that this worked because you knew that it worked in general already. Now, could you verify it worked if you were asked to do that? Sure, we could find that, right? You would have to take this derivative, and in order to find this derivative, there's a couple things you could do. You could use implicit differentiation. I know it's your favorite, right? Yeah. Or you could solve this for y, and then you could use some chain rule stuff, right? Yeah, you could. And then you could evaluate it inside of this differential equation. Agreed? But you don't have to do that on this problem because it didn't tell you to. Again, make sure you're reading what it tells you to do on the problem. That's kind of that's the moral to the story today, right? Read the directions. Okay. All right, let's take a look at the next directions because this one's different too. This one actually says we have to do what? This one says to verify and to find. So this does both pieces that we've now learned how to do. It asks us to verify something, which we've learned how to do, and it asks us to find the particular solution as well. Okay, so it kind of combines those last two ideas. All right, so for starters, let's do the finding. How's that sound? I think that's what I wrote down first that I was going to do. So let's find what our particular solution should be. And in order to do that, we're going to start with this piece of information down here. This piece of information tells us that y equals 0 and y prime equals 1/2 when x equals to 2. So let's start with what we have at the beginning, which is the information about y. So y is supposed to equal 0 when x is equal to 2. Which looks like that, right? Can I find out what C1 or C2 is at this point? No, there's too much unknown, right? I have two unknowns to still find, and so I would be still guessing pieces of information. So that sort of leaves me hanging. I have to pause on that. We'll come back to it. The other thing I have the piece of information for is that y prime equals 1/2 when x is 2. So let's give that a shot. We can find y prime, right? So what is y prime? What is it? You're going to have that part of it. Something else too, though. All right, so what is the derivative of C1? That's 0 because C is a number, right? This is a constant. This is a constant times ln x. So that C2 is still there, isn't it? right? This piece is still here, and then the derivative of ln x is the 1 over x. That's really much more helpful because there is no c1 any longer, right? So if I take the piece of information that I've blocked in red, this tells me y prime is 1/2, so that's 1/2 on the left, when my x value is 2. So if I've got 1/2 on the left, and I've got a 2 right here, what will the c2 value end up being? Yeah, c2 is 1. So all of this yields me that c2 is equal to 1. So I can take that information back up over here when I still had the c1 and the c2 both involved, and I can plug in 1 for c2. So I have 0 equals c1 plus ln 2, because the c2 value is equal to 1. So what does c1 equal? Negative natural log of 2. That's just a number, right? You know, you may not like the look of it. You don't need to find a decimal approximation. That would be changing it to being less accurate. You can leave it as negative natural log 2. So the solution that we have now found, if it is indeed, when we haven't verified it yet, but we have found the solution to be y equals c1, which is negative natural log of 2, plus c2, which is 1, ln of x. You can leave it like this. That's fine. How else could you write this? You could use the log properties. It's actually not going to be multiplied because if I write this in the correct order, I've got a subtraction. So this is actually ln x minus ln 2, which would be equivalent to ln of x over 2. So either of these versions are fine. In some sense, because I'm going to have to find a first derivative and a second derivative, it might be nicer to leave it without that because then I don't have a chain rule involved. So I'm going to go with this particular one this time, right here, simply because as I find my derivatives and my antiderivatives, it's going to be a little bit easier to work with. Okay, any questions so far? So in terms of the two things that we have to do, sort of this is issue number 1, verify, and issue number 2, find. And we have to find the particular solution. We found the particular solution first. It says verify the general solution. We can do that, but we could also verify it by using the specific solution. It's the same thing. So as we verify, you could either verify using the solution they gave you with the C1s and C2s in it, or you can verify it using the solution that you ended up with at the bottom, which might be a little bit easier to work with because it doesn't have this arbitrary letters in it. Does that make sense? So I'm going to suggest we use that particular solution as we're verifying. But if you did it the other way, of course, that would work too. All right, so we're supposed to verify that x times y double prime plus y prime equals 0, right? And we have our solution, which is y equals, I'll write it in this order, natural log of x minus the natural log of 2. Is that good? Okay, let's find the derivative. We need the first derivative and we need the second derivative. So what is the first derivative of ln x minus ln 2? One over x. Is it plus 1/2?
0.
Is it minus 1/2? Jordan says 0. So it is 0. Why?
He said it was a number.
Yeah, it's just a number. I know it doesn't look like it though, does it? It's kind of like you guys did your basic skills derivatives quiz. I know it's been ages ago now, but at some point on the quiz I had you take the derivative of something like e squared. Do you guys remember that? How many of you put down the derivative was 2e? Or was e to the 2? You used one of those rules. It's sort of natural. We kind of feel like we should be doing something with it, but just got to remember there's no variable in there, so the natural log of 2 is actually derivative of 0. All right, and then we are going to find y double prime, which might mean that it'd be helpful to see this written as x to the negative 1 for y prime. All right, so what is the second derivative for this equation going to be? Negative x to the negative 2, or we could write that how? Negative 1 over x squared. And I think for purposes of plugging it in, having it written in these forms is probably the most helpful. But you could certainly do it otherwise if you chose to. All right, so I'm supposed to verify that when I take x times y double prime, which is my negative 1 over x squared, and I add that to y prime, which is 1 over x, that I'm going to somehow get 0 out of that. All right, so let's simplify the left-hand side. What does the first piece become? Negative 1 over x. The second piece is positive 1 over x. So in fact, what happens? They're both 0. So my final step actually shows the matching on both sides. Excellent. Any questions? Yep.
Is the x 2?
No.
Okay.
Do you remember when you were working with finding antiderivatives back in Calc 1? And the first thing you did is you had all these plus c's everywhere. Do you remember that? And then there was an additional component somewhere where they said if you have an initial condition given, when x equals 5, the function equals 7, you could find the value for c. That's finding a particular solution. It doesn't mean that x is always equal to 5, but it means at some location on the curve x is equal to 5. So it's almost like giving you a curve, and you know that the curve always has the equation y equals x plus 2, or something like this. Well, somewhere along the curve, you've got the point 0, 2. It's right here. But that doesn't mean that x always equals 0, right? It just means it's one location on the curve. And that's what's going on with that ordered pair that they give you. Where was it? Yeah, in the red, right? That at some point x does equal 2, and when x does equal 2, we have this specific y value and this specific derivative. But they're not always equal to those. Good question. Any other questions on this one? Okay. All right. The last set of directions for this section, where we're practicing our reading skills, right? Or our following direction skills. What does it say we're supposed to do on these? Use integration to do what? Find the general solution. We have not found a general solution yet, have we? It's always been given to us, and we've been asked to verify it. Now, the directions actually tell you how you're going to go about finding it. There is one step ahead of what we normally have done before. This actually gives you a derivative. dy dx equals x cosine x squared, right? Okay. Here's the first thing you're going to do. The first thing you're going to do is it's going to look like you're going to multiply the dx to the other side. So I'm going to rewrite this as dy equals x cosine x squared dx. Is everybody good with that step? Okay. Next step is we're going to do an integration on both sides, like it said in the directions. So what is the integral of dy? It's y. Now the right-hand side is what you've seen before, right? You've seen things look like that all throughout Chapter 8. And this is the point where we said the integration for this is not going to be hard. How are you going to integrate this? This is u substitution. What will u be? X squared. So what is du? 2x dx. And you don't have that 2, right? So we will move that out in front. So this is 1/2. I'm going to rewrite this with u substitution. The x and the dx are going to disappear and become du, and then it has the 1/2 I already did in front. The cosine x squared in the middle is going to become what? Cosine of u. And what is the antiderivative of cosine of u? That is sine of u. Plus c. Thank you, Taylor. And u actually has a different name. It's called x squared. And you now have found a general solution. So we went from the very beginning with being given general solutions to now you've actually found one. It's kind of a big jump, actually. But it's using skills you already knew how to do, right? And the integration's a lot easier than you've been dealing with recently, agreed? Yeah, let's try another one, same directions. This one says, dy dx equals 5e to the negative x squared. What's my very first step?
Bring the dx.
Yeah. So we're going to bring the dx over or multiply the dx, however you think about that. What's my step after that? We're going to put that integral sign to integrate. The left-hand side is going to become y. The right-hand side, what are we going to do with it? We use substitution. What's u going to be, Chelsea? Right. And what will du then be? Negative 1/2 dx. Very good. Now I don't have a negative 1/2 in my problem, so I'm going to multiply that to the other side. That's going to be a negative 2. That's now going to be my problem, right? So over here I've got negative 2, well, times the 5. So can I make it negative 10? Is everybody good with that? All right. And then I have e to the u du. I like e's. Do you like e's? Sure. Who doesn't like an e? All right, what's the antiderivative of e to the u? E to the u.
Plus c.
Plus c. And then my u has a different name. It's called negative x over 2. What do you think? Think you can handle it? I think you can too. All right.